All right, we had talked just a tiny bit the other day about power functions, so I'm gonna make sure we're all good on what power functions are. And we're gonna look at this graph and see what's going on. So my question is, what power function did this graph come from, and how many zeros does it have, and what multiplicity? So that's what we want to know. So we're gonna look here, and we're gonna say, well, there's a zero here, one. There's a zero here, two, and there's a zero here. So it has 3 zeros with multiplicity 1. And I know there are 1 because they just go straight through. 1, 2, 3, right? But this guy, remember, zeros are your x-intercepts, right? They're your solutions when you set it equal to 0. So there's 1, 2, 3. But this guy is also a 0, but it has multiplicity of 2. Okay, so it has multiplicity of 2. That means that we know that because it comes down and it just barely hits the x-axis and then it bounces off. So this bounce is what tells me it's got multiplicity of 2. Okay, that's how I know, because of that bounce, that it comes down, it hits the x-axis and it bounces off. These go straight through, straight through, straight through. Straight through tells me multiplicity of 1. And if you remember the other day, I said that if it's more than a multiplicity of 1, it'll still go through, but I'll take our mind back to this guy. This guy is the nice, pretty y equals x cubed, right? Okay, so if I had that nice, pretty y equals x cubed, we know that this is the parent function, this is the original, but if it had other stuff in it, it would bounce, right? 1, 2, 3, it would go up and down more. 3 different directions, 2 different turning points. But see how instead of just going straight through, it comes up and it changes its inflection. So this one is like, it looks like it's part of a downward facing parabola. This one is looks like it's part of an upward facing parabola. And the fact that it comes through here and it changes that inflection right there, right at the x-intercept, which is at the origin in this case, that's what tells me, okay, it's going through, but it's not a multiplicity of 1. If it was a multiplicity of 1, it would go straight through, boom, straight through, straight through. This is not. It actually changes its inflection. So this guy has 1 0 with multiplicity of 3. Okay. And what happens is if it goes through, it's an odd. So like you would have something very similar to this if you just had the original y equals x to the 5th. It would just go like straight through. But it would change its inflection. It would kind of flatten out more. That one would be 1 0 with multiplicity of 5. Okay. But the way you can tell it's not a 1 is because it does this little boppy thing here. Okay. It changes direction, so to speak. Changes inflection, I should say, not direction. All right, so that's what's going on with that. Here we had the 3 zeros with multiplicity 1. So that's going to look something like this. Okay. There's an x, an x, an x. I don't know what's going on in these factors. This would be a plus something because they're negative, plus something because it's negative. Maybe that's -3 and -5. I don't know. But this one would be like an x minus 1 or something like that because it's a positive. Okay. Each of those is a multiplicity 1. But this guy right here, he's an x minus something. And we know he's squared. So when I look at this, it's 1, 2, 3, 4, 5. So his power function, let me scoot this up a little, I'm sorry. His power function is coming from add up all your exponents, add up the multiplicities. Okay, so his power function is coming from y equals x to the 5th power function. So that's what's going on there. So it's coming from that. 1, 2, 3, 4, 5. You can see it going in 5 different directions. You can see 1, 2, 3, 4 turning points. So all the stuff we've already talked about kind of comes into play, and we see it adding up to what we're doing here. All right. So that's all lovely. The next thing I want to talk about, though, is what if the original or the parent function came from f of x equals 1 over x. What if that's what we came from? So this is a different parent function than what we've talked about before. It has the x on the bottom. Everything we've talked about so far was a polynomial. This guy we know is not a polynomial. Not a polynomial. But it is a function. Okay. So this guy, whenever I say we can see he's not a polynomial, the reason why I say he's not a polynomial is because the x is in the denominator. If you remember, we said we can't do anything with x in the denominator. This is the same as f of x equals x to the -1, where its exponent would be -1. That's what makes it go to the denominator, if you remember your exponent rules. And this guy is not a whole number, right? So negative integers make x in the denominator. Okay, or you can just say, I can't have an x in the denominator. That's what's going to make me be not a polynomial. Okay, but what I'm saying is he is a function. So he's going to work pretty much the same as all of our polynomial functions have worked. It's just that his original parent graph is going to look different. So let me show you this one. I keep on scooting this up. Sorry. F of x equals 1 over x. So on the graphing calculator, I go to y equals 1 over x. That's what it looks like. And you can see it's actually got 2 pieces to it. So it's got this one down here on the bottom side and this one up here on the top side. So whenever I go to graph that guy, there's a piece down here and there's a piece up here. Okay, and when I look at that, I say, hey, when I went to go graph this, I was drawing here and I had this going down for infinity, negative infinity. And to get to the other piece, I had to pick up my pen and come up here and draw this piece. Now, each of these pieces is nice and smooth and continuous, but the entire graph isn't continuous. Sometimes if you have an older graphing calculator, it'll actually like try to connect these. It's called connected mode. Okay, it'll try to connect them and it'll give you this really weird heartbeaty thing like that, where the axes would be going through here. It's not really connected like that. It's just that your calculator is trying to do it. So we're going to try to avoid seeing that. So don't use this. This is bad. They are not connected. They are 2 separate pieces. Okay, so this is not continuous. So even if you couldn't tell by looking at the equation, the x is on the denominator, so it's not a polynomial. The graph will tell you for sure, right? So every time we see these, we're going to think, oh, that's not a polynomial. This is actually a new kind of function for us. It's going to be called a rational function. It's going to be called a rational function. And so whenever you see that, you should think like a ratio, right? Like that's the first word I see over here, ratio. Okay. So this is when basically x is in the denominator. Okay, we're going to see those. So there's two new parent functions. One is this guy, the 1 over x. And when I say parent function, you should be thinking, okay, that means that I'm going to be able to do stuff to it, right? I'm going to be able to move it. I'm going to be able to shift it and stuff like that. And that's absolutely what's happening here. So we'll be able to still do some of the transformation rules that we've done before, right? All of our shifting and stretching, stuff like that can apply here. Okay, you're just going to have to remember, if you want the horizontal shifts, that stuff's going to be in the denominator with the x, because it's got to be inside of the function. If you want the vertical shifts, you would have this guy and then like +3 or -5 or whatever. So it would be outside of the fraction in that case. So there's that guy, and then there's also this other guy. F of x equals 1 over x squared. And basically the way I think about this is kind of like the odd guy for the rationals, excuse me, because it's symmetric around the origin, right? So these are, so it's kind of like the odd guy. The exponent on the x is a -1. This one's going to be kind of like the even guy. So remember, even functions are going to be reflected around the y-axis. So when I come in here, I need to put parentheses because I want the x on the bottom to be squared rather than having the entire fraction squared. It doesn't really matter much in this case, but once I start moving things, it'll matter. And look at that. So this has also got two pieces in it, but whenever I look at it, they're both on the top. So let's think about that for a second. I'm doing x squared on the bottom. Here I had -1 over, like say if I had -2. 1 over -2 would be -1/2, right? But now I've got 1 over x squared. So the positives actually still look the same. Okay, or similar. Okay, 1 over a +2 squared would be 1/4. Okay, no problem. But on the negative side, notice it's not down here in the bottom anymore. That's because when I square them, it becomes positive, right? So for this squared guy, when I say -2, 1 over -2 squared, I get 1 over 4. So it actually ends up being this piece up here. And again, if you look at this, this is an even thing, right? So it is symmetric around the y-axis. So this is like the even parent function for all those rational functions. So that's what's going on there. Okay. So what the heck's going on here? I'm going to have to worry about domain, right? So for instance, on this guy, we cannot divide by 0. We know that. Cannot divide by 0, which means x cannot be 0. And look here, here's my x equals 0 guy right here. That's right there on the y-axis. And sure enough, x cannot be 0. It never is going to touch this, right? So we see this graph is being kind of pulled in and it's going up against it, and it's being pulled in here and it's going up against it here from opposite sides, but it's getting really, really, really close to this y-axis, but it's never actually going to touch, okay? And the same thing going on down here. So whenever I start talking about the domain down here, we're going to do x squared cannot equal 0. Remember, we set up that little inequality. X squared is not equal to 0. Here we would take the square root, but it's okay. It means x cannot be plus or minus 0 when I square root both sides. I put in the plus or minus. If it was anything other than 0, I'd be getting 2 solutions because this is an x squared guy. But because it's 0, 0 is not positive and it's not negative, so it doesn't matter. So whenever I see this, I'm like, oh, okay. It just says x can't be 0. So again, I've got this line going through here that the graph is going to come up against it. It's going to get really close on both sides, but it cannot actually equal that. So it's never gonna cross over that line. And I'm going to say never, but there are occasional places where it might. So we'll kind of talk about some of those later. But for the most part, you can talk about these pieces right here, these lines, where they're not going to hit by talking about the domain. And that tells me the asymptotes. So the word here that we're after is asymptotes. asymptotes. Okay. Asymptotes are, in our case, we're going to say lines. They can be other shapes, so they could be a quadratic or something like that. But for our purposes, it's always a line. If you got into a really advanced math class, you might see some parabolic asymptotes that are like quadratic or something, but this is not going to be that. And it's lines where the graph doesn't touch or cross. Okay. For these vertical asymptotes, those are kind of the nice ones for you to find. Vertical asymptotes happen whenever there is a bad spot in the domain that can't be removed. Okay, and what do I mean by that? Okay, occasionally, and we'll see some of these again as we work through, occasionally there may be a spot where we say, okay, there's an X on the top, there's an X on the bottom, we can divide out that X, that kind of thing. That would be a removable bad spot in the domain, okay? But in this case, I have this X squared on the bottom, for instance, or even the one up above where I just had an X on the bottom. There's nothing for it to reduce with or cancel it out, right? So nothing's going to go away here. So when you start talking about that, you're like, oh, it can't be removed. If I can't remove this, I can't, reduce it or divide it out or something like that, then that is a vertical asymptote. And that's exactly what we're seeing happen right here. Vertical asymptotes cannot be crossed. Okay. And the reason why is because they are bad spots in the domain. That means that is never going to happen. Okay. We're never, X can't be 0 here, and we're never ever going to say, except for this one time, we know we can't divide by 0, period. So that's the way that's going to go. Okay. So first off, I'd like to look at a few examples of things in the domain and what does that mean for us as far as asymptotes. So here we go. Example. We'll come back, and if we have time in this video, we will talk about horizontal asymptotes, but that's a different process. So first I want to make sure that we've got this for the verticals. So I want us to talk about domain. Okay, we've got an example, f of x equals 2x squared minus 4 all over x plus 5. Okay, so the notes might say something like find the domain, blah, 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 blah. Okay, so whenever I look at this, I say, okay, do I care about the top at all for domain issues? And the answer is no. We want to focus on the denominator. Okay, and the reason why is because we remember we can't divide by 0, right? So what that means is, in order to find your bad spot in the domain, you take the denominator. You're actually going to need to pull these out and set up the little equation and say x plus 5 cannot equal 0. Okay. Well, this one's not terrible because all I need to do is subtract 5 from both sides of the equation. Okay. X cannot equal -5. We know that. Okay. So when I go to look up here, I say, okay, if I put in a -5, what does this mean for me? Think it through. X cannot equal -5. If I put in -5 right here, -5 plus 5 would be 0. then I'd be dividing by 0, right? Okay, so this is my bad spot in the domain. And I can't remove it. I can't divide it out. So it's going to be there. So if you were doing your interval notation for this, remember it would go -infinity to -5, and then -5 to infinity. And so we would say we just can't have -5 in my domain. So that's my bad spot. Okay. That's where we are. And that's not so horrible. Whenever we look at it, we say, okay, that's a vertical asymptote. And so how do I find these things is becomes the question. Here's another example. Excuse me. F of x equals x cubed divided by x squared plus 1. Okay, so the first thing you want to do is reduce as much as possible. Okay, and that means looking for common factors. Well, there's an x cubed up here on the top, but it won't reduce, right? Because remember that this denominator is one whole thing. You've got to treat it as if it was parentheses. These are added together and you can't separate them, okay? If you wanted to divide, you'd have to divide both of them. So you can't just say, hey, I'm gonna split this out. It doesn't work that way. So, but x squared, like up here, we had this x plus 5. If somehow the top could have been factored out, and I would have had an x plus 5, that could have happened, right? Then those would be reducible. Then we talk about, okay, what's going on here? This one doesn't do it. So reduce if possible. Well, I can't find that. And then 2, find your bad spots in your domain. Okay, so this just involves doing exactly what we did earlier, which is take this denominator out, set up a little inequality, x squared plus 1 does not equal 0, and then solve for x. So that'll tell me my bad spot. Now this one is interesting because when I go to solve for x, I'm going to subtract 1 on both sides, and I get x squared cannot equal -1. I need to get rid of the square, so I square root both sides. And we know put in the plus or minus, okay? But when I do this, x, let me get rid of those squares and square roots, cannot equal plus or minus the square root of -1. Now that guy right there is an imaginary number, right? So you may know him as plus or minus I, okay? Either way, this is not a real number, right? Either way. So I can't take the square root of a negative number. That makes it not real, excuse me, or imaginary. So not a real number, which tells me the only bad spot in this domain is an imaginary number. Which means all real numbers are okay. All real numbers work. That double R right there, that's like a notation for real, okay? So that is not going to be a problem at all. I'd like to do one that I think is going to reduce. So let me, yeah, I think this one's going to reduce. Let me give you one more example, and this one we'll talk about. Stuff happens when things reduce. So the example is f of x equals x squared minus 9 divided by x squared plus 4x minus 21. Okay, now we have talked about factoring before, and hopefully you've made yourself really good at factoring, because that's just like the first step here. We kind of expect for you to be able to do it. So let's talk about the top. This is x squared, this is 9. Those are both squares, and this is a minus sign in between them. So hopefully when you see it in that format, you look at that and you say, hey, that's a difference of squares, and that will factor. So the way it factors is an x and an x. And to get to the -9, we know it should be what squared gives me 9. It's a 3 and a 3. And to get rid of the middle terms in the middle, it's +3 minus 3. Okay. So if you were to multiply this out, remember that's x squared minus 3x plus 3x. Those go away. And then +3 times -3 is the -9. So that's how that guy factors. Okay. And then this bottom guy also, I'm going to hope that you can factor fairly quickly. It's just a 1x squared out there. So I'm going to go x and x. And I'm looking for factors of 21. It's negative. So one's a positive and one's a negative. That will add up to +4. So again, hopefully you've gotten pretty good at this factoring thing. And you can look at that and say, okay, factors of 21 are 7 and 3. If it's a +7 and a -3, that'll give me a +4. So I'm going to go with x plus 7, x minus 3. All right. So there we are. We've got that going on right there. And when I look at that, I say, hey, hang on a second. Excuse me. I've got the same factor on top as bottom, x minus 3 and x minus 3. Okay. Those will reduce. Those will go away. So this turns into x plus 3 over x plus 7. That's what I meant by reduce if you can. Okay, so you may take a little bit of factoring or something like that, a little upfront work to get me there. But once I'm there, I should be able to reduce some of these. So we'll talk about this guy and what's going on with it in a second. But for my vertical asymptote, remember, now that I've got this guy, I need to pull out the denominator and I need to say x plus 7 cannot equal 0. Okay, x plus 7 does not equal 0. So now again, solve for this x, subtract 7 on both sides, x cannot equal -7. This is my vertical asymptote. That's a bad spot, okay? By the way, okay, so that's what we already talked about, but we still need to deal with this x minus 3 guy because notice, x minus 3 will still give us a bad spot. Right? In other words, if I put in, let's figure this out, x minus 3 can't equal 0, right? Let me scoot. Okay, add 3, x can't equal 3. Okay, so if I put 3 in up here in the denominator, 3 squared is 9. 9 times 4 is 36. Hang on, I'm sorry. X minus 3 can't equal 3. Should be a negative, maybe? X squared 4 times 3 is 36. Hang on, sorry. 4 times 3. Oh, 4 times 3 is 12. That's my problem, not 36. I was doing the 9 plus the 9, that's my 21, minus a 21, I get 0, right? So it helps if I put in a 3 there and not the 9. That's what I was doing in my head. So anyway, 9 plus 12 is 21, minus 21 is 0. So this guy still gives me 0 on the bottom, and that's a problem. I can't have that. So this is a bad spot, but it's removable. Okay, that is not a vertical asymptote. When they're removable, it's called a hole. Okay, so literally what that means is if I go to graph this equation, which I'll do it in a second, if I go to graph this equation, then I'm going to see a vertical asymptote at x equals -7. Okay, that's definitely a vertical asymptote. But when we get to x equals 3, I am not going to see a vertical asymptote there. I'm going to see a hole. So what that means is literally like the graph is going along, it skips that particular spot, and then it keeps going, okay? It's literally a hole. And that's why they call it a removable discontinuity. If I could just fill in that spot, this graph would just be continuous, right? So it's called removable, and it's a discontinuity. Okay, so let's look at this and see what the heck am I talking about. So what we think is we should have a vertical asymptote at -7, and we should have a hole there. So let's plug this guy in. And to do it, I'm going to put in parentheses, x squared minus 9, close my parentheses, that's my top, divide by, and again, I'm going to use parentheses because I wanted this to make sense. I wanted all this stuff to stay in the bottom. So it's x squared plus 4x minus 21. Okay, that's what that is, x squared plus 4x minus 21. All right, there we go. Look at that. Okay, so we had this piece of the graph going up. We do have, this is what I was talking about. Sometimes it tries to connect it. That is not part of my graph. That's actually the vertical asymptote. It's trying to connect a point up here with a point down there. And then here is this, but notice that when we get to x equals 3, it doesn't show anything weird. So in order to find that, what you would need to do is go into the table, which is up here above your graph button, second graph, and look right here. At 3, I've got an error, okay? It should be also, if I go to -7, there it is, I've got an error. So when you see these things, if you're looking at your x values and your y values and you see these errors, know that those are the spots that are problems in the domain, right? So that's exactly what has happened here. When we get to the 3, we see an error because you can't stick 3 into this guy. It gives you a bad spot. That's the error, okay? So remember that. Your calculator says error, okay? All right, but that is not a vertical asymptote. That one is just a hole. Okay, and I don't really have time to talk about horizontal asymptotes right this second. We'll come back to them. But notice that all of these graphs also have some horizontal asymptote stuff going on. For instance, the one we just drew, these points are not going below a certain point, and these points are not going above a certain point. So the horizontal asymptotes, occasionally you can cross them in the middle. But the nice thing is that asymptotes have to be adhered to in the end behavior. So we'll remember that as we go out towards the end. You may be able to cross a horizontal asymptote occasionally in the center, but you're not going to be able to cross that horizontal asymptote in the end. So that the end behavior is what's important there. All right, that's it for now. I'm out of time, but hopefully this video helps. All right, let me know if you have questions. Thanks. Bye.